So what we have seen so far is this background on a probabilistic mixture model and how do you do inference calculations and parameter learning the parameters of this mixture model from data points that are given to us, right. We have spent a great deal of time that we will now make the final connection of how this mixture model actually underpins the soft k-means heuristic or algorithm. We will essentially be re-deriving the same algorithm that we had presented before using an intuitive formula, and you may wonder why we have to go all the way around and touch the nose around because we already derived the soft k-means algorithm before, and so why do we have to go through this mixture model route. The important part about this whole session that I would like to emphasize again is that once we understand this mixture model connection, then we can actually improve the mixture model, enhance this mixture model, and that will automatically lead to enhancements to the k-means algorithms that we have. So, we will be able to design new variants of the soft k-means using this understanding of the mixture model. Okay. So, it is worth our extra time to spend a few more minutes trying to understand what is the connection between soft k-means heuristic that we have seen before and the underlying mixture model that we have seen in this background. Okay. So, this slide summarizes this connection. Okay. We said that the soft k-means clustering is just figuring out a bunch of you are given n objects or n data points, right. So, n data points, right, and then you want to group them into k objects or k centers, right, and then you want to figure out this fractional responsibility of each center for each data point, right, and that is exactly this Rk of n that we used to call before. Okay. But this parameter learning of a mixture model and then associated inference is essentially you want to figure out this theta hat MLE, these 5 parameter mixture model, right. So, these are all these 5 parameters, and where the correspondence between these two is what we used to call as clusters here is called a component in the mixture model. So, we have a component here, we had k clusters here, cluster centers, we have k components here, right, and then your theta hat of MLE will tell you how the data is being generated, all of these parameters that will explain how the data is being generated, right. Then once you know the theta hat of MLE that this EM algorithm has given you using this maximum likelihood approach, then you can calculate again your probability that zk equal to n, zk equal to, zn equal to k, given that you have observed the data point xn and then using your current best set of parameter theta hat MLE. And this is essentially equivalent to this responsibility vectors Rk of n. Okay. So, whatever was the responsibility here is this probability calculation here that comes from the inference on this mixture model, right. So, this is how the two things are related. The k clusters here are the k components, right, and then the k centers here are given by these different parameters mu1 and mu2, right. Mu1 and mu2 are these centers, and we will just assume that sigma 1 equal to sigma 2. Assume this just for simplicity, so that the different components have the same variance, then the different components are distinguished only by their means or centers. Okay. So, then that k centers here, so the k clusters are the k components, and the cluster centers here, the different cluster centers are the means of these different components. Your clustering problem, you are interpreting it as inferring the hidden cluster labels or component labels. So, hidden cluster labels or component labels in the mixture model of two Gaussians. Okay. Another simplification we are going to actually do is the following, okay, which is, so let us take a stock of all the simplifying assumptions we have made, okay, and then maybe add a few more also. So, one of the simplifying assumptions we have made is that we are going to look at a mixture model of 1D Gaussians, okay, and so that really means that the dimensions over which our data points are is I is equal to 1. Okay. So, initially we said that x of n is in I dimension. So, each of the x of n is an I dimensional vector. So, you are looking at I genes, but here we are only going to look at one gene. Okay. So, that is this this gene A here, and then we had this 4 data points, and then we had this, right. And then given these 5 data points alone one dimension, we want to infer the hidden cluster labels, we want to do this parameter learning, to figure out this curve, and then this inference calculations to figure out what is the responsibility vectors. Maybe for this is 0.9 comma 0.1, and then for this data point responsibility vector is 0.2 comma 0.8. Okay. So, that is your inference calculations. Okay. Inference and the parameter learning to figure out this curve, right. So, this is a first simplifying assumption. The second simplifying assumption is that we said that each of these components C1 and C2, which had this mu1 comma sigma 1, and then in mixing proportion pi 1, and C2 is the parameters are mu2 comma sigma 2, a 1D Gaussian with those parameters with mixing proportion pi 2 equal to 1 minus pi 1, right. We said that let us just forget about sigma 1 and let us just learn the mean alone. Okay. So, all of those sigma 1 equal to sigma 2, we are just going to assume, these are all these assumptions, we are going to assume that this is equal to the same sigma, and then it is known. Okay. We know what the spread is, okay, for each of the components in our mixture model. So, simplifying assumptions about our Gaussian mixture model. Okay. We can later relax those assumptions, but this is our simplifying assumptions. Okay. The third thing is that without any a priori knowledge, we will not know what is the mixing proportions to begin with. So, in that case, your pi k is simply going to be all the same, right, and you can set it to be 1 over capital K. So, this is the EM algorithm that we have seen again before in action, okay, where we have the E step or the assignment step where we calculate the responsibility vectors, and the M steps where we update the theta t to theta t plus 1, right. And now, if I were to kind of make some changes to this EM algorithm, I can go ahead and remove this theta k, right, because that theta is already known, and then pi k is going to be 1 over k, right. So, I do not have to worry about pi k also. So, this pi k is also not something to be worried about, right. And then, so this pi k is all set to be 1 over k, right. So, I do not have to really estimate it, that is also assumed to be known, okay. And then this is also sigma, this is also sigma, right. You can see that there is already a lot of simplification, so it makes it very simple. Let me also remove all of these examples here, which was for a general mixture model of two 1D Gaussians, but you are now going to look at a very simplified model, right, where sigma k equal to sigma for all k, right, is assumed to be known. Similarly, also pi k equal to pi for all k for all of the components is also assumed to be known, and that is in fact exactly equal to 1 over capital K, right. So, known value is 1 over capital K, right. The sigma value is some positive number, right. So, some positive variance. Okay. Now, if you have this, then it's a very simplistic looking formula here, right. So, this is going to be mu k is going to be this weighted variance. So, let me just put these things in this different things. So, these are the ones that I have added now, right. And then this is my weighted weights for the fractional weights, right, fractions or weights for each of the data points. So, instead of having a sample mean, I have a weighted sample mean as before. And then I have this Rk of n, which is the simplified formula. We can even simplify it further if you just take it, right, this Rk of n vector, we have this, and then we take it, we can simplify it further. This is a normal PDF, right. So, this is going to be 1 over sigma root 2 pi e to the minus x minus mu k squared, okay, over 2 sigma squared divided by the same thing in the numerator, k prime equal to 1 to capital K. Capital K was 2 in our examples. We were fitting 2 components, can also fit more than 2 components, right. But this will be 1 over sigma root 2 pi e to the minus x minus mu k prime. K is all changed with k prime now, whole square divided by 2 sigma square, right. And again you can see here that let me use a different ink again. This part and this part will get cancelled, right. And let us say that you want to define, let us say beta is defined to be 1 over 2 sigma square, then you will see that because it is in 1D also, x minus mu k whole squared is really the squared Euclidean distance between 2 points, right. So, if mu k is over here, so if this is your mu k, right, and then this is your data point, right, this is your x. So then this is the distance x minus mu k, and then you can square the distance, and that is going to be that is what we initially defined as d of x comma mu k, right. So this is essentially the squared distance. We defined it using the letter d, right. And so this x minus mu k whole squared is going to be d. So if I just do those two things, beta equal to defined as 1 over 2 sigma squared, and then x minus mu k whole squared, which we defined as d of x comma mu k, then you have e to the minus beta d of x comma mu k divided by sum over k prime in from going from 1 to capital K, e to the minus beta d of x comma mu k prime, right. So this is the simple looking formula. So what we have is that in the E step or the assignment step, where we are calculating this responsibility vector, if we make those simplifying assumptions where sigma k equal to sigma and that is known, and then pi k equal to pi and that is also known, right, and then your dimension is also I equal to 1, right. So we used to think of x of n as in r to the I, but let us say I equal to 1, that is another assumption. So if you make all of these assumptions, then your Rk of n turns out to be this very nice looking softmax formula, right, where you take all the distances of a data point x. In this particular case, this is the data point x we are interested in, and then you look at its distance to every one of the cluster centers, and then you convert those set of distances into this set of probabilities, right. So this softmax function in fact comes out to be the result of calculating this probability, this inference on this mixture model, okay. That is the connection I want you to see. And once that is done, then everything else in the M step of the EM algorithm are exactly same as before, except for the simplifying assumptions we have made to make sure that we are just dealing with a simple case of the M step, okay. Now if you put these two steps into the pseudocode, then you have a vanilla soft k means exactly like what we had before, okay. So now we can see here that this equation here, Rk of n, the soft version, e to the minus beta distance of m of k xn and sum over k prime e to the minus beta d of m of k prime comma xn. The only change between this and this equation is that I have called mu k to be m of k, right. So the only renaming is that mu k is now called as m of k, but otherwise this formula, this plus is exactly the same as this formula. This is also the same plus formula, okay. So this is our inference that we have done using this mixture model. So if you know your theta t, that is going to be your mu 1, mu 2, right, essentially those two, right. So mu 1 and mu 2, or this is also defined as this m of 1 and m of 2, right. If you know the current value, then you can use that to calculate your responsibility vectors, and then in the update step you are going from theta t to theta t plus 1. So you are just updating essentially your m of 1 and m of 2 again if there are only 2, if capital K is 2, okay. And that is what is being done in the update step, and this formula, right, this formula star is exactly the same as this formula star. This is the star formula, right. So you have the plus formula here, the star formula here, that comes from the EM algorithm to do a parameter learning of a mixture of two 1D Gaussians, right, and that exactly turns out to be what we have seen as vanilla soft k means before, right, this plus and this star formula that is in the assignment and the update step, okay. So this completes the connection we have established between soft k means clustering and parameter learning of a mixture model of two 1D Gaussians, okay. The only thing that is left is how to go from 1D Gaussians to more dimensional multivariate Gaussians, okay. That is what we will look at next. That is the final detail, right. So the same algorithm works for multiple dimensions also. If we assume that the Gaussians across the I dimensions are independent, right. So what do we mean by that? So if x is in R to the I, where I is greater than 1, right, then you look at each of the dimensions separately and assume that there is an independent 1D Gaussian operating along that dimension, okay. And so if you have p of x given the component is z is k prime comma theta, theta captures all of these parameters in the model, then it just simply product along all these dimensions pi I equal to 1 to I, right, p of xi, that is the I dimension of this data point given z equal to k prime, that the k prime component is generating this data point comma theta. Okay, this is true for any cluster k prime. Okay, so for any cluster k prime to generate a particular data point, you just have multiple 1D Gaussians along each dimension that are independently generating the data point. So that the probability of the overall multi-dimensional data point is going to be the product of the each dimension being generated by component k prime. Okay, and this is true for any cluster k prime. Okay, so this is what the assumption means. And so now how will the likelihood change from 1D to I greater than 1D? It will remain very similar. Okay, if you use this notation of distances as squared Euclidean distances, like the d notation, probability that x is this x, where x is an I-dimensional vector, given theta equal to all of these, instead of 5 parameters, now you have or the simplified set of parameters, now you have multiple parameters. So pi 1 through to pi k, m1 through to mk, and sigma, right? So you have sum over k prime equal to 1 to k, pi k prime 1 over sigma root 2 pi. This is the normal PDF, right? And then you expand it out and you simplify like we have done before. I am not going to go through each of these steps, but you can see that this comes out to be again e to the minus beta d of x comma m of k prime. Okay, and this is what we have shown for 1D, right? Now for multi-dimension, this particular for multi-dimension, so this, right, this is going to become increased by a factor of I, because there are I dimensions that you have to multiply, and then this one remains the same, right? So if you see here, in here you just have one dimension, so x minus m of k prime whole square, this is just 1D, but here you will have multiple dimension that you have to sum over, but that is already taken care of by this d. So the final formula looks the same. So d of x comma m of k prime, whether x and m of k prime are in 1D or x and m of k prime are in multiple dimensions, this handles it nicely. So the only difference is that you have sum over k prime pi of k pi k prime, this is multiplied by a factor of I, and then this distance remains the same. This distance is between these 1D data points here, but here the distance is between these I dimensional data points. Okay, where you are just summing over all the dimensions and doing the square difference between xi and mi of k. Okay, everything else remains the same. So it is beautifully extends to I greater than 1 dimension. So you don't have to change anything at all. Again, if you make the simplifying assumption that pi k prime are all the same, right, then your Rk of n remains the same formula, right? It is just simply e to the minus beta d of m of k comma x n divided by sum over k prime e to the minus beta d of m of k prime comma x of n. Okay. So this same algorithm that we just saw here for one dimension, this was derived using the assumption of one dimension, right? That exactly applies for I greater than 1, more than 1 dimensions also. So if you are working with 1 gene or 2 gene or 70 genes or 1000 genes, the vanilla soft k-means algorithm that is derived by using this EM algorithm, right, applied on a mixture model is exactly the same. Okay, that is what this slide shows. And this particular form of responsibility vector that this slide shows, right, is exactly what we have also intuitively derived before, right, which is this: we have these 3 distances and then we use the softmax function to convert those distances into these probabilities that add up to 1, and that also perfectly matches. So we have these kind of 3 things that are triangulating, right? So we had this intuitive formula and then used that to derive our soft k-means. We have this mixture model and used it to derive the soft k-means. Both of them are identical. Is what we have seen. Okay, that is the connection we have established. So now that we have established the connection between soft k-means clustering and the mixture model or a probabilistic mixture models parameter learning in great detail, let's go ahead and use that and exploit that connection to address the remaining 2 pitfalls of k-means that we have not addressed so far. Okay, so what we have addressed so far is we have addressed this fuzzy assignments for data points that are in between 2 clusters. We have made soft k-means to fuzzily assign it to both the clusters. But what we have not fixed is this large and small data sets. So this is large and small in 2 ways. This is large in terms of one is having a lot more proportion than the other one, and then one is also having more spread than the other one. So we have this large and small data set. And the second part is this long and narrow lozenges data set. Okay, we will address it each one at a time. Okay, and that will give you 2 new variants of k-means that will address these 2 points, 2 pitfalls.